Good day, grade 12 learners. Welcome to today's physical sciences lesson. My name is Amini Mkize. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Remember, grade 12s, you can interact with us via WhatsApp. Our number is 0795782908. And remember, learners, when you interact with us, please do not send us voice notes, videos. Just, type, and then we'll be able to assist you, right? Grade 12 learners, today the focus is on paper 1, under which knowledge area electricity and magnetism. And under electricity and magnetism, remember, we have 3 topics there: your electrostatics, your electric circuits, and your electrodynamics. So the focus today, learners, is on electrodynamics, right? Right, under electrodynamics, learners, according to your CAPS document, or according to your examination guidelines, these are the things that you need to know under electrodynamics. 1, know the energy conversions in generators. Use the principle of electromagnetic induction to explain how a generator works. Explain the functions of components of AC and DC generator. State examples of the uses of AC and DC generators. State the energy conversion in motors. Use the motor effect to explain how a motor works. Explain the functions of the components of a motor. State examples of the motors. State the advantages of alternating current over direct current. Sketch graphs of voltage versus time and current versus time for an AC circuit. Define the term root mean square for an alternating voltage or current. Solve problems using the equations IRMS equals to Imax over root 2, VRMS equals to Vmax over root 2. Also solve problems using the equations or the formulae P average equals to RMS, VRMS, which is equals to half V max multiply that by Imax. P average equals to I squared, RMS multiplied by the resistance, which is your R there. And P average equals to V squared RMS divide that by the resistance. So this is what you need to know under electrodynamics grade 12s, right? Then terminology, these are the terms that are very, very important, learners, when it comes to electrodynamics. A generator, remember a generator, we have seen a generator before, right? So you should know that a generator, that is a device that converts mechanical energy to electrical energy. Know how to state Faraday's law. You did this in grade 11. The magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in magnetic flux, or in magnetic flux linkage. Fleming's right-hand rule. Remember, we use Fleming's right-hand rule when it comes to finding the direction of the induced current when it comes to generators, or we are going to look at that. Then that is Fleming's right-hand rule. Then motors, an electric motor, that is a device that converts electrical energy to mechanical energy. Fleming's left-hand rule, we use Fleming's left-hand rule for motors. For generators, we use Fleming's right-hand rule. And then for motors, we use Fleming's left-hand rule to find the direction of rotation of the coil, because when it comes to motors, it's about rotation of the coil. When it comes to generators, it's about the induced EMF, right? Then the conventional current, we know that from electric circuits, that the current flows from the positive terminal of a cell or a battery to the negative terminal, right? Then AC, that is an alternating current, so the direction of current changes after each half turn, right? And then DC, that is the direct current. The current direction is constant, right? And then the root mean square potential difference. So we are still going to talk about that. Then peak potential difference, which is also known as maximum potential difference. It is the maximum potential difference value reached by the alternating current as it fluctuates, right? The root mean square current, all right? So we are still going to talk more about that. And then the peak current, which is also known as the maximum watt current. Then the symbol there is Imax, right? That is the maximum current value reached by the alternating current as it fluctuates, right? So that is the peak current. So these are the terms that you need to know under electrodynamics learners, all right? Then grade 11 revision. Remember in grade 11, I think you did touch on this, learners, that remember when it comes to a current carrying conductor, right? Around a current carrying conductor, there's what magnetic field, all right? Around current carrying conductor, there's what magnetic field. So if you can check here, you are having a straight conductor, right? And in that straight conductor, there's current that is flowing through, all right? So since there's current that is flowing through that conductor, then current induces what? The magnetic field, all right? And how do we find the direction of the induced what? Magnetic field? We use right-hand rule, right, to find the direction of what? Of the induced magnetic field. So around, current carrying conductor, there's what? Magnetic field. So current induces what? The magnetic field. And to find the direction of that magnetic field around that conductor, we use right-hand rule. All right. So how do we use right-hand rule? Right. So your right-hand rule, check on this diagram, right? So the thumb here, this is the thumb. The thumb is always in the direction of what? Of current, and then the curled fingers, they will give you what? The direction of the magnetic field. So if you're using your right hand and you want to find the direction of the induced magnetic field around current carrying conductor, then we have to use right hand rule, all right? So if the current is out of the page, right? So out of the page, for example, when it comes to this diagram, right? Remember, we can represent out of the page. So this is out, we represent out by a dot. So this dot gives you what? The direction of what? Of current, all right? The cross also gives you what? The direction of what? Of current. So but the dot is, that is current out of the page, current out of the page, that is the dot, and then current into the page, we use a cross for that, all right? So to find the direction of the induced magnetic field, we use right hand rule, and then the curled fingers, remember, they're in the direction of the magnetic field, and then the thumb is in the direction of what? Of the current. So around current, so there's current already here, so around current carrying conductor is what? The magnetic field. So to find the direction of the magnetic field, you use your right hand. So using your right hand here, like it or not here, because the current is out of the page, look at the curled fingers, right? So this is out of the page, all right? So look at the curled fingers, then this will be the direction of what? Of the magnetic field, right? So that is going to be what? Out of what? Of the page, okay? So it's out of the page. Look at the direction of the magnetic field. The direction of the magnetic field, you just follow the what? The direction of the curled fingers, all right? So that is out of the page, and then into the page is this diagram, all right? So look at that diagram. So the cross represents what? Current into the page, and then the dot represents current out of what? Out of the page, all right? So look at the direction of the magnetic field there. So this is current into the page. So if current is current into the page, then the direction of the magnetic field will be this. So it will be what? In this case, it will be, clockwise. So here it will be clockwise, and then here it will be what? Anti-clockwise. So here it should be anti-clockwise, right? So by now we know this, or we did this in grade what? In grade 11, that around current carrying conductor there's what? Magnetic field. So current actually induces what? The magnetic field, all right? Current induces what? the magnetic field. So to find the direction of the induced magnetic field, we use right-hand rule. Then when you use that right-hand rule, the thumb is in the direction of the current, and then the curled fingers are in the direction of what? Of the magnetic field. It's what we have to use to find the direction of the induced magnetic field. So current induces what? The magnetic field, right? Then, so here is still right-hand rule, all right? I've explained that already, right? And this is what the magnetic field around a loop. So this is a loop, all right? So if you can check here, the current here is what is in, all right? And then the current on this side is what is out, all right? So there's current that is flowing through this loop, or there's current that is flowing through this conductor, right? So to find the current, to find the direction of the magnetic field, again, we use right-hand rule, right? So where the current is in, right? So remember, we represent that by a dot, all right? So not the dot, but the cross. So the cross represents the current in, and then the dot represents the current out. So if you check this side, the current is what is in. So if the current is in, then the direction of the magnetic field, so it's into the page, right? So the current is in, then the direction of the magnetic field will be what? Clockwise, all right? Then this side where we are having B, right, or side B, the current here is what is out. So if the current is out, then what about the direction of the magnetic field? The direction of the magnetic field will be what? Will be anti-clockwise. So there's nothing that is difficult here, learners. You just use your right hand. So current induces what? The magnetic field. So how do we find the direction of that magnetic field? We use right hand rule. So the dot and the cross, please do not confuse the two. The cross, remember, is for current into the page, and then the dot is for current out of the page, not other way around. All right. Then let's move to electromagnetic induction, right? What is electromagnetic induction? Again, I think we did touch on this in grade 11, but let me just remind you. Remember, in the previous slide, we said current induces the magnetic field, all right? So current induces what? The magnetic field, or current produces what? The magnetic field, right? Then, similarly, changing magnetic field induces what? Electric what? Current. Changing magnetic field induces what? Current. So current induces the magnetic field, and the magnetic field, or the changing magnetic field, will induce what? Current. So that is simple. That is actually electromagnetic what? Induction. So current induces the magnetic field, then at the same time the changing magnetic field will induce what? Current, right? So that is electromagnetic what? Induction. So learners, let's look at this diagram, right? In this diagram, what are you having? We're having the bar magnet there, right, with its poles, the north pole and what? And the south pole, right? And then we're having a coil there. This is a coil, right? And then this is a what? A magnet. So remember, a magnet produces what? The magnetic field, right? So then if you can check here in this diagram, both the magnetic field and the coil are stationary, right? So if both the magnetic field and the coil are stationary, no EMF will be induced in that coil, right? That is why we are saying a changing magnetic field will induce what? Current, right? Changing magnetic field. But if you check here in this diagram, the coil and the magnetic field are what? Are stationary. So there is no relative, movement between the coil and what? And the magnetic field. So since there's no relative movement between the coil and the magnetic field, no EMF will be induced in this coil. So how are you going to see that there's no EMF induced in this coil? One, look at the voltmeter reading. The voltmeter reading there is what? It's 0 volts, right? So if the voltmeter reading is 0 volts, what about this bulb? Is it going to light up or not? It won't light up because there's no, EMF induced in what? In that coil. When will be EMF induced? If there is relative motion between the magnetic field and what? And the coil, right? So, but if there is no relative motion, both the magnetic field and the coil are stationary, no EMF will be induced in what? In that coil, right? But as long as now there's that relative motion between the coil and the magnetic field, then EMF will be induced in what? In that coil. So which means that if we can move this magnet in and out of the coil, right? So now there will be that changing magnetic field, right? There will be that relative motion or movement between the coil and what? And the magnetic field. So then EMF will be induced in that coil. And that is what we call electromagnetic what? Induction. So you can't talk about electromagnetic induction if there is no relative motion between the coil and the magnetic field. So when do we talk about electromagnetic induction? It's when now the coil and the magnetic field are what? Are moving relative to each other, right? So which is either the coil moving, the magnetic field stationary, or the magnetic field moving, the coil stationary. So as long as we are having that relative motion between the coil and the magnetic field, then EMF will be what? Will be induced. And how are you going to see that the EMF is induced in this coil now? Then there will be a reading now on what? On the voltmeter reading. So on the voltmeter, right? So there will be a reading on the voltmeter. Then how are you going to see that there's EMF induced also? Then the bulb now will light up. All right. So the bulb will what? Will light up. So, but when are we going to have EMF induced in a coil? If there's what? Relative motion between the coil and what? And the magnetic field. And that is what we call electromagnetic what? Induction. All right. Then the induced what? EMF. Remember, induced EMF. Remember, EMF is induced if there's that movement or relative movement between the coil and the magnetic field, right? And that induced EMF, right? That induced EMF, it is what? Directly proportional to the rate of change in what? In magnetic flux what? Linkage, right? The induced EMF is directly proportional to what? To the rate of change in magnetic flux what? Linkage, right? So you can increase this induced EMF, right? By increasing the number of what? Of turns, right? You can increase this induced EMF, by increasing the speed of what? Of movement of that magnetic field. So if you can move the magnet in and out of the coil faster, the induced EMF will also what? Increase. If you can use a stronger magnet, right? The induced EMF will what? Will increase, right? So if you can increase the number of turns or windings in what? In a coil, right? Or if you can increase the number of coils, what will happen to the induced EMF? The induced EMF will what? Will increase, right? And that is what we call Faraday's what? Law. Okay? So you must know how to, define Faraday's law, right? The induced EMF, it is directly proportional to what? To the rate of change in magnetic flux what? Linkage. But remember, EMF is induced in a coil, right? If there is relative motion between the coil and what? And the magnetic field. So if we are having that changing magnetic field, EMF will be induced in what? In that coil. And that induced EMF, remember, it is directly proportional to the rate of change in magnetic flux what? Linkage. And that is what we call Faraday's law. All right. So this will assist us to check how actually we can increase what? The amount of EMF induced in what? In a coil. For example, if we increase the number of turns or windings in what? In a coil, or number of coils, right? The EMF induced will what? Will increase, right? If we use a stronger magnet, the EMF will what? Will increase. If we use what? We use a stronger magnet. I've talked about that. If we increase the number of turns, right? The EMF induced in a coil will what? Will increase. Even if we increase the speed of movement of that bar magnet, right? We push the magnet in and out of the coil faster, then the induced EMF will what? Will increase, right? So that is electromagnetic induction and what? And Faraday's law, right? So learners, there are two electrical machines that we're going to focus on when it comes to what? Electrodynamics. We are going to focus on what? On generators and what? And motors, all right? So what is a generator? We have seen a generator, right? Already when we're looking at the terminology, we have defined what? A generator. So a generator, that is a device that converts what? Mechanical energy to what? To electrical energy. All right. So it converts mechanical energy to electrical what? Energy. And then generators, they are based on which principle? They are based on electromagnetic what? Induction. How do generators generate what? Electricity, right? As long as there's that relative motion between the coil and the magnetic field, EMF will be induced, or electricity will be induced, or current will be induced in what? In that coil. So which means that generators that are based on which principle? They are based on electromagnetic what? Induction, right? Then there are two types of generators, learners. We are having what? AC generator and what? And the DC generator. AC, remember, stands for a alternating current, and then DC is direct what? Current. So there are two types of generators. It's your AC generator and what? And your DC what? Generator. All right. And learners, whether the generator is AC or DC, it converts electrical energy to what? It converts what? Mechanical energy to what? To electrical energy. Whether it is AC or DC, energy conversion is from what? Mechanical energy to what? To electrical what? Energy. Then to find the direction of the induced what? Current, or the direction of the induced current, we use Fleming's right hand rule. All right. So I will show you how to do that, right? But to find the direction of the induced current, when it comes to generators, we use which rule? Fleming's right hand rule. Okay, so those are our generators. Then that, as I've mentioned, that there are two types of generators. We have AC generator and the DC watt generator. So this is just a simple structure of what? Of an AC watt generator. How does it look like? Here you are having what? The magnets, right? So you have magnet this side, you have a magnet this side, north pole, south pole, all right? What is the function of this magnet? Remember, it produces what? The magnetic field, okay? You are having a coil there, right? You have a coil, that blue, what? A conductor, it's a coil, or you can say it's a conductor or an armature, right? So we are having a coil there, and then you have this. You can see these rings. These are the rings, ne? So what is the name of these rings? It's slip rings, right? We call them slip rings, all right? We call them what? Slip rings. And then we are having the brushes here attached to those slip rings, all right? So we are having brushes there attached to those slip rings, all right? Then we are having what? There, a bulb, right? So a bulb will indicate whether the EMF is induced or not induced in what? In a coil, all right? But how does a generator work? Remember, a generator, it's based on which principle? Electromagnetic what? Induction. As long as we are having that relative motion between the coil and the magnetic field, right? EMF will be what? Will be induced in that coil. So here, this is what a simple structure of what? Of an AC generator. So the magnet there, so the magnet produces what? The magnetic field. Then there are slip rings, all right? There are brushes attached to those slip rings, and then you have what? That bulb there, which will indicate whether EMF is induced or not induced in that coil, all right? So learners, what is the function of what? Of slip rings, all right? Slip rings, they ensure that, I'm talking about the slip rings, ne? They ensure that current in the external circuit changes direction after each half turn, ne? Right, so that is the function of what? Of slip rings. So slip rings ensure that the current in the external circuit changes what? Direction after each half turn. So what makes a generator to be an AC generator? It's slip rings. What is the function of the slip rings? They ensure that the current in the external circuit changes direction after each half turn. That is the function of what? Of a slip ring. So what makes a generator to be an AC generator? It's what? Slip rings, right? Then, to find the direction of the induced current, all right? To find the direction of the induced current, I've talked about that already. Ne? To find the direction of the induced current, we use what? A Fleming's right-hand rule for generators, right? So when you use your right hand, all right, so the thumb is in the direction of the force, whether the coil will move up or down, all right? And then the not the middle finger, but the index finger, right, is in the direction of the magnetic field. So wherever your index finger is pointing, it should point to the south pole, because remember, the magnetic field lines, they run from north pole to what? To south pole. So wherever your index finger is pointing, it should point what? South pole. Then the middle finger, right? The middle finger, that is the direction of what? Of current. So the middle finger is the direction of current, whether the current is in or out. The index finger, that is the direction of the magnetic field. Wherever your index finger is pointing, it should point what? The south pole, right? And then the thumb is in the direction of the force, whether the coil will move up or what? Or down. All right. So we use what? Fleming's what? Right hand rule for what? For generators, right? Then position of a coil, right? Position of a coil, if you can check on this diagram, right? The coil is in the vertical what? Position, right? So if a coil is like this, it's in the vertical what? Position, right? As shown in the diagram alongside, zero EMF is induced in that coil, right? Zero EMF is induced in that coil. If EMF is zero, even current will be what? Will be 0 amperes, right? So if the coil is in the vertical position, learners, you must know that zero EMF is what? Is induced, or there's no EMF induced in that coil, as you can see in this diagram. So if the coil is in this position, right, you should know that zero EMF or no EMF is induced in what? In that coil, or 0 ampere or what? No current will be induced in what? In that coil. The reason being is because the normal to the plane, right? The normal to the plane of the coil is perpendicular to what? To the magnetic field, right? The normal to the plane is perpendicular to what? To the magnetic field. Then the change in magnetic flux linkage will be 0 Weber, right? Hence, what? The induced EMF will be what? 0 volts, and the induced current will be what? Will be 0 volts. All right? So, when the coil is in the vertical position, 0 EMF is induced, or 0 current is what? Is induced. Why 0 EMF is induced or 0 current is what? Is induced? Is because the normal to the plane is perpendicular to what? To the magnetic field. And when the normal to the plane is perpendicular to the magnetic field, the change in magnetic flux will be what? Will be 0, right? Why change in magnetic flux will be 0? Remember, how to calculate magnetic flux? It's given by BA what? Cos theta, right? Where theta is the angle between what? The normal to the plane and what? And the magnetic field. So if you are saying the normal to the plane is perpendicular to the magnetic field, normal to the plane perpendicular to the magnetic field, it means that theta here will be what? 90 degrees. And cos of 90 degrees, it's what? It's 0. We are aware of that. You can even use a calculator to confirm that. So which means that here, this will be what? Will be 0 Weber, right? So if this is 0, according to this equation, E equals to what? Negative N change in phi over change in T. If this is 0, this is negative N times 0 over change in T. It means that your V will be what? Will be 0 volts. All right? So you should know that if the coil is in the vertical position, 0 EMF is induced or 0 current is what? Is induced. All right? Why 0 EMF or no EMF is induced is because the normal to the plane is perpendicular to what? To the magnetic field. So if it is perpendicular to the magnetic field, then change in magnetic flux will be what? Will be 0 Weber, right? And if change in the magnetic flux is 0, what about EMF induced in that coil? It will be what? It will be 0, right? So let's move to the next one. When now the coil is in the horizontal what? Position, as shown in the diagram alongside, right? So the coil is in the horizontal position now. So if the coil is in the horizontal position, you should know that maximum EMF is induced, right? Maximum EMF is what? Is induced, or maximum current is what? Is induced. Because EMF and current, they are directly what? Proportional according to the equation I equals to what? IR. You are aware of that, right? So EMF is the maximum when the coil is in the horizontal what? Position. So maximum EMF is induced when the coil is like this, as shown in the diagram, right? So maximum EMF is induced, maximum current is what? Is induced. Why maximum current is induced is because normal to the plane of the coil, it is what? Parallel to the magnetic field. And if it is parallel to the magnetic field, what about the angle between the magnetic field and the normal to the plane of the coil? BA, right? BA cos what? Cos theta, right? So it will be BA cos what? Our theta now will be what? Will be 0 what? Degrees. If the normal to the plane and the magnetic field are parallel to each other, right? And then we know that cos of 0 degrees, you can even press your calculator to confirm cos of 0 degrees is going to be what? 1. So which means that this will be what? Will be the maximum, right? So if the coil is in the horizontal position, let's not forget that maximum EMF is induced, maximum current is what? Is induced. Why maximum current is induced, or why maximum EMF is what? Is induced, is because normal to the plane is parallel to the magnetic field. And if the normal to the plane is parallel to the magnetic field, magnetic flux or change in magnetic flux will be the maximum. And if change in the magnetic flux is the maximum, what about the induced EMF? The induced EMF will be the maximum also. Very, very important. All right. Then the graph of induced EMF versus the position of the coil, right? So check the position of the coil. This is number 1. That is the vertical position. As you can see, I've explained that already. Horizontal position, vertical position, that is your number 3. Number 4, what horizontal position. Number 5, vertical what position, right? So when the coil is in the vertical position, 0 EMF is induced. As you can see here, there's 0 what? EMF, right? Then the coil is in what? The horizontal position, maximum. So here, learners, we are having what? Maximum what? EMF, right? That is why there we are having V max. So maximum EMF is what? Is induced, right? So number 3, the coil is in the vertical position, 0 EMF is what? Is induced, all right? So 0 EMF is induced. And learners, remember, this is what? An AC generator. In an AC generator, there are slip rings. What is the function of the slip rings, right? Is to ensure that the current in the external circuit, it changes what? Direction after each half turn. So this is half turn. From this point to this point, that would be half turn, all right? Then you can see that after each half turn, what happens to the direction of the induced EMF? It changes what? It changes, right? So then number 3, you are having what? Vertical position, 0 EMF. Number 4, horizontal what position? Maximum what? EMF, but now in the opposite what direction? So we are having negative what here? V what? V max, right? Negative V max. But this negative, we are not saying EMF is negative, but we are saying EMF has changed what now? Direction. So this is going to be what? The opposite what? Direction. Then position E, that is vertical position, all right? So that is vertical what? Position. Then vertical position, 0 EMF is what? Is induced. And you can see that current alternates here. Current changes direction. Why current? So why EMF? Because here is EMF versus what? Versus the position. So why EMF changes direction is because of those slip rings found where in the external what? Circuit. Okay, so the slip rings, they ensure that the current in the external circuit changes what? Direction. All right, so this is the graph of the induced EMF versus the position of the coil. This corresponds to a graph of what? Of current, right, which is current in amperes, And then here it can be the what again here, the position, right? So same shape, right? So this will be your position 1, position 2, position 3, position 4, and then this one will be position what? Position 5, all right? So same shape, but the values will be different because up there you are having maximum voltage, and then this one will be maximum what? Current. So this will be I max. This will be what again here? Negative I what max. So same shape, right? Remember, if potential difference is 0, current is also going to be what? 0. So the graphs, the shape of the graph will be the same. What will be different is only what? The values, because you have potential difference for the first graph, and then for the second graph you have what? Current. So those are different physical what? Quantities. All right. Then a DC generator, right? So we also have a DC generator. So this is a simple structure of a DC generator, right? So when it comes to a DC, same thing, you have the magnet, right? You are still having that bulb to, you know, to indicate whether the EMF is induced or not induced in what? In a coil. So if the EMF is induced, right, in a coil, obviously it should be induced if the coil is in the horizontal position. Then the bulb will light up, right? But when the coil is in the vertical position, remember 0 EMF is induced, then the bulb won't light up, all right? So it's what will happen even when it comes to what? A DC generator. But what is the difference, the structural difference between an AC generator and what? And the DC generator? When it comes to a DC generator, there is that ring, right, which we call it what? A split ring, or you can call it what? A split ring commutator, or you can just say it's a commutator. But the correct name is split ring what? Commutator. So that is the structural difference between what? An AC generator and what? And the DC what? Generator. So here there is what? A split ring commutator, and you can see it's different from the slip rings, all right? It's different from the slip ring. So this is what? A split ring commutator. Then the brushes attached there, all right? So the brushes, remember, they make contact, so that induced current also flows in the external what? Circuit. So when it comes to an AC generator, they make contact with the slip rings to ensure that the current also flows in the external what? Circuit, right? Then when it comes to a DC generator, they also make contact, but now they make contact with the what? The split ring commutator, right? To ensure that the current also flows in the external what? Circuit, all right? So that is the function of what? Of the brushes. Then here there's a split ring commutator. So this one, it ensures that current in the external circuit flows in one direction. It doesn't change direction. Right, so that is the function of what? Of the split ring commutator. It ensures that the current in the external circuit flows in what? In one direction. So the external circuit, it's where you have, this is your external what? Circuit. Ne? So the external circuit, even the what? The split ring commutator. So that would be your external what? Circuit. So the function of a split ring commutator when it comes to a DC generator, it ensures that the current in the external circuit flows in what? In one direction. But when it comes to an AC generator, there are slip rings. And what is the function of the slip rings? They ensure that the current in the external circuit changes direction after each what? Half turn. All right? It changes direction after each what? Half turn. Those are the slip rings when it comes to an AC generator. When it comes to a DC, there is a what? A split ring or split ring commutator. What is the function of a split ring commutator? Is to ensure that the current in the external circuit flows in what? In one direction. That is why here you will see that the current here does not change direction. Up there you are still having what? Maximum Vmax, right? Maximum current, what? Maximum voltage, because this is EMF versus what? the position of what of the coil. So here obviously this will be vertical what position, 0 EMF, right? And then there it will be what horizontal position, maximum EMF, just like that. Or maybe let's go to the next slide so that you'll see this, right? So this is vertical position, 0 EMF. Horizontal position, maximum what? EMF. That is why we're having maximum there, right? Then vertical position, which is this one, number 3 there. This is 1, 2, 3, 4, then what? 5. So vertical position, 0 EMF. So remember here, there is what? A split ring commutator, which ensures that the current flows in one direction, all right? So you can see that current didn't change direction here, right? So if the current has changed direction, then this point was going to be below the horizontal axis, right? So since it is not below the horizontal axis, it means that the current did not change what direction. The current flows in what? In one direction, right? So you can see that then this is number 3 here. Then your number 4 horizontal position, maximum what? EMF. Number 5 there. So this is 1, this is 2, this is 3, this is 4, then this is what? 5. So the difference between your AC and your DC generator, AC, they are slip rings to ensure that the current what changes direction after each half turn. The current changes what? Direction. Then when it comes to a DC generator, current flows in one direction. Why current flows in one direction is because of that split ring what? Commutator, right? So this can be like this, right? Or corresponding graph, same thing, right? So there you still have your what? Your induced what? EMF. Then there you will have your Vmax there. Vmax, and then versus what? The position. Right? Even your graph of current versus what? Versus the position. Alright? Same shape, it's just that now you will have a current, and then for the other graph it will be what? The potential difference. Alright? So that is the difference between your AC generator and your DC what? Generator. But whether it is AC generator or DC, it converts what? Mechanical energy to electrical energy. Alright? Then whether it is AC or DC generator, both they are based on which principle? Electromagnetic what? Induction. Then to find the direction of the induced current for both, we use what? Fleming's right hand rule. So the difference is only that when it comes to your AC, there's a slip ring, right? When it comes to your DC, there's what? A split ring what? Commutator. So that is the difference between the two, right? Then another thing which is very, very important, learners, I've talked about the current in the external circuit. The current in the external circuit, right? Where you are having the bulb, let me just go back. Right. Yeah. So the current, I want to erase this. Right. So all right. So the current in the external circuit here, because of the slip rings, right? It changes direction. But current in a coil, learners, current in a coil, right? Current in a coil changes direction. If the current is in, then the other side, the current will be what? Will be out. Okay? So if the current is in this side, this other side, the current will be what? Will be out. So what am I trying to say to you is that the structural, actually, what is different here is the current or the direction of current in the external what? Circuit, right? When it comes to an AC generator, because of the slip rings, the current alternates. It changes direction. But when it comes to a DC, because of the split ring commutator, the current flows in one direction. But when it comes to current in the internal circuit, current in a coil, the coil that rotates through that magnetic field, the current alternates for both generators, right? So for both generators, the current in a coil, it changes what? Direction. For both what? Generators. So if the current is in, actually it's because of the shape of what? Of the coil. It's a rectangular shape. So which means that if current is in this side, this other side of the coil, it will be what? Out. So that is why I'm saying the current alternates in a coil. Check even when it comes to your DC generator, right? When it comes to your DC generator, right? So when it comes to your DC generator, right, there is also what? A coil. Because of the shape of the coil, if the current is in this side, on that other side, it will be what? Out. So what am I trying to say? Current, whether it is AC or DC, current in a coil alternates. It changes what? Direction. The difference is in the external circuit, where we are having your slip rings, your split ring commutator. So your slip rings, right, current still alternates in the external circuit, right? But your split ring commutator, current flows in one what? Direction. But in a coil, current alternates for both what? Generators. The difference is in the external what? Circuit. I hope we are together there, learners. Right. Okay, how can we increase the amount of the EMF induced in a coil? We can increase the amount of EMF induced or current induced in a coil by increasing the number of turns or windings in a coil. You should know this by using a stronger magnet to increase the strength of the magnetic field, and also by increasing the speed of rotation of the coil or the magnetic field. Right? So this is how we can increase the amount of EMF induced in a coil, or the amount of current that is induced in what? In a coil. Right? Then this is just the summary of electric generators. Both of them are based on electromagnetic induction, right? And then we have AC, we have DC, right? So we have AC, we have DC, right? And then your AC makes use of slip rings, and then this one commutator, the DC, then the AC in the external circuit, right? DC in the external circuit, right? But in a coil, both it's AC, current alternates, all right? Right, current what alternates. Then these are the uses, learners. You need to know the uses of AC generator and the uses of what? Of DC what? Generator. So the uses, it is used in power plants, right? Charging the batteries, portable power, and microphones. So you should also know the uses according to your examination what? Guidelines. Then the uses of DC, bicycle and torch, dynamos, right? Changing what's not changing, but charging what? Batteries, right? So those are the uses of what? Of DC what? Generator, right? But whether it is AC or DC, they're based on what? Electromagnetic induction, EMF, and current is induced in a coil. Then generators, they convert mechanical energy to what? To electrical what? Energy. All right? Then motors, right? Motors, they convert electrical energy to mechanical what? Energy, right? Then they're based on what now? Motor effect. They convert electrical energy to what? To mechanical energy. They are based on which principle? Motor effect. So I will explain motor effect. Again, learners, you're having two types of motors. It's your AC motor and what? And DC motor. Then remember here, learners, it's about rotation of the coil, right? So how can we find the direction of rotation of the coil? Whether the coil rotates clockwise or anti-clockwise. We use Fleming's what? Fleming's left-hand rule. So it's Fleming's left-hand rule for what? For motors, and then Fleming's right-hand rule for what? For generators. But your motors, they convert electrical energy to mechanical, while your generators, they convert what? A mechanical to electrical. Generators, they're based on which principle? Electromagnetic induction. What about motors? They're based on which principle? Motor effect. All right? Then two types of generators, AC generator, DC generator. Two types of motors, AC motor, DC what? Motor. Right. Then to find the direction of the induced current when it comes to generators, you use your Fleming's right-hand rule. Here, to find the direction of rotation of the coil, we use Fleming's left-hand rule. All right. Then this is a DC motor, a simple structure of a DC motor, right? So the difference between your DC generator and your DC motor, right? It's just that here, when it comes to a DC generator, energy conversion is from mechanical to what? To electrical. Here is from electrical to what? To mechanical. That is why there we are having a source of what? A source of power. All right? But whether you are having DC generator or DC motor, you have the split ring what? Commutator. So when it comes to a DC motor, there's a split ring what? Commutator. What is the function of this split ring commutator? Is to ensure that the coil, remember here now the motor, right? The motor, it's about rotation. I hope you have seen a motor before, right? For example, when it comes to your fan, right? When it comes to your CD player, when it comes to a washing machine, when it comes to a microwave oven, right? There is a motor there. So motor actually is about rotation, all right? So what is the function of a split ring commutator when it comes to a motor? Is to ensure that the coil rotates in one direction. Remember, the split ring commutator when it comes to a generator is to ensure that the current flows in one direction. Here, what is the function of a split ring commutator? Is to ensure that the coil rotates in what? In one direction. Coil rotates in one direction. That is the function of what? Of a split ring commutator when it comes to what? A motor. So here, learners, there's a source of power, right? Remember, we are converting what here? Electrical energy to what? To mechanical energy. So we need a source of what? Of power to provide electrical what? Energy. All right. So there's a split ring commutator here, but what is the function? The function is to ensure that the coil rotates in what? In one direction. Then we use Fleming's left-hand rule to find the direction of what? Of rotation of the coil, right? So the force is still the thumb, whether the coil will move up or down. Then the index finger, that is going to be what? The direction of the magnetic field. And then the middle finger, it's in the direction of what? Of current, right? So I want to explain motor effect, learners, right? Motor effect. Okay. Motor effect, remember, let me just go back. Right. Let me erase this. Okay. So this is our DC what generator. I want to explain how a motor works, right? Because I did explain how a generator works. Né? So we are saying a motor, the basic principle for motors is what is motor effect. So what is motor effect? Remember, learners, there's current that is flowing in this coil because of that source of power, right? And we know that around current carrying conductor, there is magnetic field. Current induces what? Magnetic field. So there's current that is flowing here. Remember, there is that source of power there, all right? So there's current that is flowing through this coil. Then, since there's current that is flowing, remember, current induces what? The magnetic field. So this coil actually will experience how many magnetic fields? Two magnetic fields. Why am I saying that? There will be magnetic field due to current in this conductor, right? There is also magnetic field due to what? To the magnet. So there are two magnetic fields experienced by this coil. There is magnetic field due to current. There is magnetic field due to the magnet. All right. So this coil experiences how many magnetic fields? Two magnetic fields. So two magnetic fields, then magnetic force will be what? Will be produced, right? So this coil actually will experience what? A force because of those two magnetic what? Magnetic fields. Then if it experiences a force, then it will either move up or what? Or down. So then the coil will start to do what? To rotate. So that is actually motor effect. So this coil experiences how many magnetic fields? Two. It's magnetic field due to what? To current in a coil, and there's magnetic field again due to the magnet. So it will experience how many magnetic fields? Two magnetic fields. Then it will start to do what? To rotate. So what makes it to rotate? It's the force of repulsion between those two magnetic fields. All right. Then what? A coil will start to what? To rotate. So here it's about rotation of the coil, but when it comes to generators, it's about the induced what? EMF, right? So that is motor effect in simple words, right? So motor effect, the coil experiences two magnetic fields. It's magnetic field due to current and the magnetic field due to the magnet. Then a coil will experience a force. And what type of a force is this one? It will be the magnetic force, and then the coil will start to do to rotate. All right. Then so that is motor effect. So to find the direction of rotation of the coil, whether the coil will rotate clockwise or anti-clockwise, Fleming's left-hand rule. All right. Then this is an AC motor. So what is the difference between AC motor and the DC motor? When it comes to AC motor, right, we have what here? The slip rings. Same with the AC generator. So here we have what? The slip rings. So these are slip rings. And then there's a source of power because electrical energy must be converted to mechanical energy. All right. So there's a source of power. Same with with a DC motor. Source of power, right? But what is the difference is that when it comes to your DC motor, there's a split ring commutator which ensures that the coil rotates it in one direction. But here there are slip rings which ensures that the coil changes direction. So the coil changes direction. So the coil changes direction. Coil changes direction. Why the coil changes direction when it comes to an AC motor is because of the slip rings. So I hope you can see the difference now that when it comes to an AC generator, the function of a slip ring is to ensure that the current in the external circuit alternates or it changes direction. Here, the function of a slip ring when it comes to a motor is to ensure that the coil changes direction. All right. So it's about rotation here. So how can we increase the efficiency of a motor? Right. Efficiency of a motor can be increased by using a stronger magnet. Right. We can also use you can increase the number of turns in a coil, or increase the number of windings, or increase the number of coils. We can increase power, right? Or we can use a source of power with high voltage. So that is how we can increase the speed of rotation of the coil. So you can increase the speed of rotation of the coil, or you can increase the efficiency of a motor by increasing the number of coils, increasing power, or using a source of power with high voltage, and also by using a stronger magnet. So here it's about rotation of the coil when it comes to motors. When it comes to generators, it's about what is this? The induced EMF. All right. So please do not confuse the functions. Yes, we understand that when it comes to an AC generator, AC motor, there are slip rings. But what is the function of a slip ring or slip rings when it comes to generators? What is the function of slip rings when it comes to motors? How can you see that this is a generator, this is a motor, this is an AC generator, this is an AC motor? AC generator, there's no source of power. AC motor, there's a source of Of power. Slip rings in both. But what is the function of a slip ring in a generator? What is the function of a slip ring in In a motor? That is very, very important in us to identify that, right? Then this is just the summary of motors, right? Both of them, they're based on On motor effect, right? So there's a source of power, right? So the source of power here is the DC source, right? Of power. Then here it's alternating current source. Then energy conversion for both is electrical to mechanical, right? And then this one, it makes contact with the slip rings and the brushes when it comes to DC. When it comes to AC, there are slip rings, right? Then these are the uses. The uses, smaller appliances like your CD players, your computers, pens, laser printers, right? And also electric trains. So those are the uses of DC motor. AC motor, appliances needing large power. For example, heavy industrial machines. They make use of Of AC motor. You also need to know the uses of these two types of motors. All right. Then this is just a summary of both electrical machines, your generators and your motors. So It's what? A generator, a motor, then generators. Remember to find the direction of the induced current or the induced what EMF. We use Fleming's right-hand rule. To find the direction of rotation of the coil when it comes to motors, we use Fleming's left-hand rule. Then generators, whether it is AC or DC, they're based on electromagnetic induction. And then motors, whether it is AC or DC motor, they're based on motor effect, which is the fundamental what principle. Then they convert mechanical to electrical. Those are your generators. Motors, they convert electrical to what? To mechanical. Then we're having a DC a generator and a DC motor. Both of them, they have split ring commutator, right? But note that the functions are not the same, right? The functions are not the same. Although it's split ring commutator, but remember the function of a split ring commutator in a generator is to ensure that the current in the external circuit flows in one direction. What about the split ring commutator when it comes to a motor? Is to ensure that the coil rotates in one what? Direction. Whether it is AC motor, AC generator, there is what? Slip rings. What is the function of a slip ring when it comes to an AC generator? Is to ensure that the current in the external circuit changes direction, right? But when it comes to a motor, is to ensure that the coil changes direction as it rotates. Ne? So that is very, very important. So this is just the summary of both machines. Ne? Then multiple choice questions, because you will also get multiple choice questions when it comes to your generators and motors, or when it comes to your electrodynamics, right? So let's look at this one. The sketch below represents an alternating current generator. You are told that this is what? A generator. What type of a generator? An AC generator. Which one of the following is correct about an AC generator? Right? Which one is correct? So let's check. A generator converts mechanical energy to electrical. That is correct. Electrical to mechanical, it can be, right? We know it converts what? Mechanical to electrical energy. C, electrical to mechanical, it can be. D is correct because it's mechanical to what? To electrical energy. Then type of ring used when it comes to an AC. Is it slip rings? Yes. Is it a split ring commutator? No. Right? Is it a slip ring? Yes. Is it a split ring commutator? No. So where you're having two ticks, that will be your correct answer. I hope you understand why B can't be the correct answer, why C can't be the correct answer, why D can't be the correct answer. So the correct answer for this one will be what? Will be A. As long as you know your AC generator, your DC generator, your AC motor, your DC motor, the functions and all that, you will be able to answer such questions, right? Then the device that uses electrical energy to produce mechanical energy. So electrical to mechanical. So this one we know it should be what? A motor. A motor converts electrical energy to what? To mechanical energy. So a dynamo, it's a generator, this one. So it's one used of what? Of an AC generator. So this one converts what? A mechanical. So here is from mechanical to what here? To electrical. An alternator, right? That is an AC generator. Name? Right? So this one is DC. This one is what? Is what? Alternator. That is what? An AC generator. Another name for an AC generator. That is an alternator. Ne? So again, it converts what? Mechanical to what? To electrical. So it can't be correct. Right? A generator, we know mechanical to what? To electrical. Then an electric motor, it converts electrical to what? To mechanical. So this one will be the correct will be the correct answer. So a dynamo, it's an example. Check on that table that I gave you, that I talked about. I'm not sure which slide, but a dynamo, that is an example of a DC generator. So obviously a generator, it converts mechanical energy to what? To electrical energy. Then an alternator, that is an AC generator, right? Then it converts again mechanical energy to electrical energy. Then an electric motor, electrical to mechanical, which is what we are looking for. Generator, mechanical to electrical, so it can be. So the correct answer for this one will be what, learners? Will be C. All right, so you can see how easy questions are when it comes to what electrodynamics, as long as you know your story. All right. Then what about this one? A DC generator, right? This is a DC what generator, functions at frequency of 80 hertz, right? The number of times the output voltage reaches a maximum in 1 second is. So actually here, what are they looking for, learners? Is you actually to know the meaning of 80 hertz, right? One, what is frequency? Remember, frequency says the total number of waves or total number of vibrations passing a point per watt per second, right? Which means that if you have let me just use this one. If you have 1 hertz, this is equivalent to 1 watt per second, 1 wave per second, right? Or 1 vibration for watt per second. If you're having 80 hertz, right, this is equivalent to what? To 80 per second, or which is going to be what? 80 waves per watt per second. So when it comes to what generators here, we talk of what? The number of times the output voltage reaches a maximum in 1 second. So 80 hertz is equivalent to what? To 80 cycles per watt per second. 80 watt full turns per watt per second. All right. So that is the meaning of 80 hertz. So which means that the number of times the output voltage reaches a maximum in 1 second is still what? 80. So the correct answer here will be what? Will be C. So you need to know the meaning of 1 hertz or the meaning of 80 hertz. So 80 hertz is equivalent to 80 waves per second, to 80 vibrations per second, to 80 full turns per watt per second. All right. So, or 80 turns per watt per second. So that is the meaning of what? Of 80 hertz, right? Then this one, the diagram shows the variation in EMF produced by a generator. So they can ask you what type of a generator can produce such graph, right? It can be a DC generator, because with a DC generator there's a split ring commutator which ensures that the current does not change direction, or the current flows in what? In one direction. But if you check this one, the current alternates. All right. So this, like it or not, it should be what? This one, an AC what? Generator. This should be an AC generator. Why are we saying an AC generator? The current or the EMF alternates, or it changes what? Direction. If the armature or the coil of the generator is rotated as twice the speed, how will the EMF and the period shown by the graph change? Right? So here, remember we talked about things that we can do to increase the amount of EMF induced in what? In a coil. And one of the things that we can do to increase the amount of EMF induced in a coil, it was to increase what? The speed of rotation of what? Of the coil, right? And remember, if we increase the speed of rotation of the coil, speed is given by F what? F lambda, right? So if we increase the speed, right? If we increase the speed, what will happen to what? To frequency. The frequency will also what? Increase. Then frequency and period, they are what? Inversely proportional. All right? So one, we are increasing the speed. So if we increase the speed, what will happen to frequency? Right? If we increase the speed by the factor of 2, right? We increase the speed of rotation by the factor of 2. This one will also increase by the factor of 2. All right? Then if this has increased by the factor of 2, what about T? T will decrease by that factor, because F, it is what? Inversely proportional to T. Frequency is inversely proportional to what? To period, right? But one, we know that if we increase the speed of rotation of the coil, EMF will be increased also. So the EMF will increase, right? What about the frequency? The frequency will also what? Increase by that factor. So you increase the speed of rotation by the factor of 2, right? What about frequency? The frequency will also increase by the factor of 2. But if the frequency has increased by the factor of 2, what about period? Period will decrease by that factor. So that is very, very important, and it's what you have to know, learners. So let's check. What are they looking for here? What will happen to EMF? EMF will increase. What will happen to period? Period should decrease, right? So let's check. So let's go back. So the EMF was 10. So we are expecting the EMF now to be greater than 10 because we've increased the speed, which increases the amount of EMF induced in a coil, right? So it will be greater than 10. So we'll come back to period. So greater than 10, it can't be equals to 10, it can't be less than 10 because we're increasing the speed of rotation of the coil, which will increase the EMF induced in that coil, right? So let's check the period. Right. So let's check the period. So what will happen to period? We said frequency will increase, right? Frequency will increase by the factor of 2, but here they're not asking us about the frequency, but they're asking us about what? About the period. Ne? So if it was frequency, we were going to get something like this. But higher than, should be greater than 10, this one. Frequency, right? So the frequency will increase. So there were how many waves that we're having in 0.2? It was 1. But now, because we've increased the speed by the factor of 2, now we are going to have how many waves? 2 waves in how many seconds? 0.2. So we can see it's 1, then what? 2. Because we've increased the speed by the factor of 2, frequency will also increase by the factor of 2. Which means that if we're having only one wave, because this is half plus half, that is 1 full 10, right? So we're having 1 full 10 before in 0.2 seconds, right? Then if we increase the speed by the factor of 2, now we are going to have how many full 10s in 0.2 seconds? It should be what? 2 full 10s, right? But what about the frequency? Sorry, not the frequency, but the period. Frequency and period, they're inversely what? Proportional. Then are we expecting the period to be more than 0.2 or less than 0.2? It can't be more because the period should what now? Should decrease. Remember, what is period? Period is the total number of waves, not the total number of waves. Remember the total number of waves per second, that is the frequency, ne? So what is period? That is the total time taken to complete one full cycle. The total time taken to complete what? One full cycle. So what was the total time taken to complete one full cycle before? It was what? 0.2, right? We have increased the speed by what? By the factor of 2. Frequency will also increase by the factor of what? Of 2. That is why we will have what? 2 waves in how many seconds? 0.2 seconds, right? Because we've increased that by what? By the factor of what? Of 2. But what about the period? If we increase the speed by the factor of 2, period will, not the period, but the frequency will increase by the factor of 2. But what about the period? It will be 1 over 2. So we are having 1 over 2 for period. Why 1 over 2? Because frequency and period, they're inversely what? Proportional. So it's 1 over 2, then you multiply that by what? By 0.2. Then you'll get what here? 0.1 seconds. All right? You'll get 0.1. So let's check where we are having what? 0.1. I hope you understood this. We are increasing the speed of rotation by the factor of 2. Frequency will increase by the factor of 2. But what about period? It will decrease by that factor. It will be 1 over 2 because frequency and period, they're inversely what? Proportional. All right? So that is why here I'm having that 0.1. So the period now will be less than before, right? So let's check. So obvious here, it can't be 0.2. It has to change. It will be 0.1, 0.1. It can't be 0.4, right? It was going to be 0.4 if we're decreasing the speed by the factor of what? Of 2. Then frequency decreased by the factor of 2. But period increased by the factor of what? Of 2. So the correct answer here is going to be what? B for this one, right? So I know that one was a bit challenging, but as long as you know those equations, you'll be able to answer that question. Then again, structured questions on motors. So learners, this is the motor, right? There's a source of power there you can see. What type of a motor is this one? It will be a DC. Why DC? What makes this motor to be a DC motor? It is going to be what? The split ring what? Commutator. You can see there's a split ring commutator there. So a source of power plus a split ring commutator, that makes what? The motor to be what? A DC motor. So they're saying 2.1, name the principle on which motors operate. All of us, we know it's a what? A motor effect, right? State the energy conversion. When it comes to motors, electrical energy to what? To mechanical what? Energy. So simple questions. Give a reason why section BC in the above diagram does not experience a magnetic force, right? In which direction will, so this one, the reason why it does not experience the magnetic force is because they're talking about BC. The reason why BC will not experience the magnetic force, I'm not talking about the EMF, right? EMF will be induced and there will be maximum EMF induced here. Why maximum EMF? You can see the coil is in the horizontal position, right? So, but this side won't experience the magnetic force because this side is parallel to the magnetic field. Look, this is the magnetic field, right? From north to south. So since this side is parallel to the magnetic field, that side won't experience what? The magnetic force. It is parallel to the magnetic field. It won't experience the magnetic force. So it means that it's only this side, right, where we're having AB, side AB, that would experience the magnetic force because that side is perpendicular to what? To the magnetic field. So when do what a coil experience the magnetic force? The coil will experience the magnetic force if that section, for example, section AB is perpendicular to what? To the what? To the magnetic field. But if that side is parallel to the magnetic field, it won't experience what? The magnetic force. So please do not confuse the magnetic force with the induced EMF. There's maximum EMF induced here. But what about the magnetic force? BC won't experience what? Any magnetic force because of what? It is parallel to the magnetic field. Then this side ABCD will experience the magnetic force. The coil will either move upward or down, which shows that it will experience what? The magnetic force. Why it will experience the magnetic force? It's because that side ABCD is perpendicular to what? To the magnetic field. So you have to know that. Then in which direction will the coil rotate? Clockwise, anti-clockwise? Then learn us to get that. Use your Fleming's left-hand rule because this is the motto. Use Fleming's left-hand rule. Then you'll be able to do what? To get the direction. Right. Write down one way in which the turning effect can be increased. How can you increase the turning effect here? How can you increase the speed of rotation of the coil? Use a stronger magnet, right? You can use a stronger magnet. You can increase power. You can use a source of power with high voltage. You can also increase what? The number of turns or the number of coils or the number of windings in what? In a coil. So it's what? So here to get this, you have to use your what? Your left-hand rule, Fleming's left-hand rule, because this is what? A motor. So please do not confuse the two, learners. Right. Then this is a simplified sketch again, which represents what? A motor, right? So what type of a motor is this one? Again, check. There is a what there? A split ring commutator. So again, this is going to be what? A DC what? A DC motor. Then to get the poles, you can see there's B, there's A there. So to get the poles, you have to use again Fleming's what? Left-hand rule, because this is what? A motor. All right. So this is the motor. Name the electrical component in the above motor that ensures that the coil rotates in one direction. So already I've explained that we are having a motor there. What type of a motor? It will be a DC motor because of the split ring commutator. We are aware of that name. Then the component that ensures that the coil rotates in one direction only. That component I've explained, it is what? A split ring commutator. The function of a split ring commutator when it comes to a DC motor is to ensure that the coil rotates in what? In one direction. Done. So the component which is responsible for that, it is the split ring commutator. Split ring commutator. Then identify the polarity of the magnets A and B. Right? For you to get that, you have to use what? Your Fleming's what? Left-hand rule, because this is what? A motor. So you have A as your north and B as what? As the south pole. But to get that, Fleming's left-hand rule, it's a motor. Then another important part when it comes to your generators and motors is alternating current. Know the definition of the root mean square current and the root mean square what? Voltage, right? So what is the root mean square what voltage or root mean square potential difference? It is an AC potential difference which dissipates or produces the same amount of energy as an equivalent DC potential difference. So that is how we define your root mean square potential difference. The root mean square current is the alternating current which dissipates or produces the same amount of energy as an equivalent direct current, which is your DC. Then, so that is your root mean square current and your root mean square potential difference, right? So we can calculate the root mean square potential difference and the root mean square current. So to calculate the root mean square potential difference, we use this equation where you are having Vmax over root 2, and then here is Imax over what? Over root 2. What is Imax? Is the maximum current in amperes. What is IRMS? Is the root mean square current in also in what? In amperes. What is VRMS? That is the root mean square potential difference in volts. What is Vmax? That is the maximum or the peak. So sometimes they can say the peak voltage, peak current, maximum current, peak voltage or peak potential difference. That is the maximum potential difference, which is measured in in volts. Then average power is given by VRMS, IRMS. Average power is also given by I squared RMS times R. So P average is V squared RMS over over R. So these are the equations that you can use to calculate the average power. And please, learners, do not use P equals to VI. P equals to VI, we use this when it comes to electric circuits. So these are the equations that you need to use under electrodynamics. So equations for electrodynamics. These are the equations or the formulae for electrodynamics, learners. Let's not forget. So if you are going to use P equals to VI, you will lose all the marks. So please be careful. Remember, you can't just write VI. We don't know whether it is Vmax or VRMS. So you need to be specific. Which potential difference are you talking about? Which current are you talking about? Is it the root mean square current or the maximum current? So that is why it is very, very important to use these equations as they are. All right. Then, so here they are just explaining the equations. VRMS, what is VRMS, Vmax, Imax, P average, and all that. So that is another thing that you need to know. Advantages of using AC over DC. These are the advantages, and they will ask you about those advantages. So AC voltage can be stepped up or down using transformers, and AC can be transmitted over long distances at high voltage and low current to minimize energy loss due to to heat. And it is cheaper to use to produce AC rather than to produce DC. So these are the advantages of using AC over DC. Questions, these are the structured questions. You will get multiple choice questions, right? When it comes to electrodynamics, so out of that 10 multiple choice questions, 1 or 2 of those questions will be on electrodynamics, but in most cases it's just one question. So, but you will still get questions, multiple choice questions on electrodynamics, and also a structured question, which is in most cases is your question 9, right? So your question 9 when it comes to your paper 1, right? So this question, the diagram below illustrates how electricity generated at power station is transmitted to a substation, right? So you are given that diagram there. So how electricity is being generated, all right? So this is what a generator. Does power station use AC or DC generator? So learners, you must know that power stations, they use what? AC generator, because it is easier it's cheaper to do what? To produce what? AC. Again, AC voltage can be stepped up or what? Or down. That is why at power stations they're using what? AC rather than using what? DC generator. So they use what here? AC. Then sketch a graph of potential difference generated at the power station versus time. So what are they expecting here? Already you have mentioned that at the power station they're using AC. So you can sketch the graph of what? Of potential difference and time. So obvious, if they're using DC, right? If they're using, sorry, not DC, but if they're using AC, the current will alternate. Then you can draw a graph like this one. Then, because they didn't indicate how many full turns we need to show, so you can just draw, as long as it is a graph of potential difference versus time and the current alternates, that will be correct. Whether your graph is like this, it doesn't matter, as long as it is the graph of potential difference versus time, right? And the current, or the potential, not the current, but the potential difference alternates. Then you will get a mark for that. The average power produced at the power station, it's 4.45 times 10 to the power 9. So this is 4.45 times 10 to the power 9 watts. We are given the average power. Calculate the root mean square current in the transmission line if the power is transmitted at the maximum voltage of 30,000 volts. So here you are given what? You are given what? The average power. You have that, which is 4.45 times 10 to the power 9, right? And then you are also given what? The maximum, Vmax, the maximum voltage, which is what? 30,000 volts, right? Then they're looking for what? IRMS, right? So they're looking for that. So how are we going to get that IRMS? So IRMS, since we are given power, right? So let's go back. So to that equation, right? These are the equations, learners, right? I want to erase here. Right, so these are the equations. So you want the IRMS. So this is the equation that you can use. Right, so this is the equation that you can use to calculate your IRMS, right? This is another equation that you can use to calculate your IRMS. This is another equation that you can use to calculate your IRMS. So, but with this one, you will have how many unknowns here? There will be two unknowns. You don't have resistance, you don't have IRMS, you only have what? Average power, right? Even, let's check with this one. You have average, you are looking for this. You can get this because you are given the Vmax, right? So you can start by calculating the VRMS, right? So it will be what? Your VRMS, right? Equals to Vmax. You copy the equation as it is, divided by what? By root 2. So what is your Vmax? You are given Vmax, ne? So the Vmax, they said, is 30,000. Then you divide that by root 2. Then you get your what? Your VRMS in what? In volts, right? Then after getting your VRMS, you are given average power. So you can use average power equals to what? IRMS multiplied by what? A VRMS, or VRMS multiplied by RMS. Then already you are having power. We are told that is 4.45 times 10 to the power what? 9. Then IRMS is what we are looking for. IRMS, we are looking for that, root mean square current. Then we are having your root mean square voltage as what? 30,000, right, over what? Over root 2. Then what about your I, right? Your IRMS will be 4.45 times 10 to the power 9. You divide that by what? 30,000, right, over what? Over root 2. Then you'll get your answer in what? In amperes. So you just work what around, and then you just use those equations, and then you'll be able to do what? To get your answers, right? And then it's just that we don't have enough time, but let's check the last question. Give a reason why electricity should be transmitted at high voltage and low what? And low current. Why should we transmit it at low voltage and what? And high at high voltage and low current to minimize a what energy loss, right? That is the reason why we have to do what? To we have to what? Transmit electricity at what? High voltage and what? And low current. So I think we have to stop here for today, but we have covered everything under what? Under electrodynamics. So the calculation part, I don't think it will be a problem as long as you are going to practice more, right? You will see how easy to do calculations on what? On electrodynamics. But please, learners, stick to your data sheet. So the equations that you have to use for electrodynamics is equations under alternating what? Current, right? So thank you very much, grade 12. Enjoy your day. So we have to stop here. Bye-bye.